Okay, hello and welcome to another video, this time taking you through what is solving a differential equation using the method of substitution. This is actually part of the further maths course once you get into, I think it's in core book 2. It might even be though in further pure 1, I can't remember, so some of you may not cover it in your further maths courses. But it comes up all the time on step, or it used to come up all the time on old step, and I think it will still come up on step 3 a lot because it's part of further maths and it's just such a classic technique. It's one you should really be aware of even if you're not going to do that part of the further maths course. I can't remember exactly which part of the books it's in. I've got a vague feeling now it might be further pure 1 where they get you to solve differential equations with a substitution, but it's a standard technique and this question is not that bad if you're aware of the technique. It's not that bad at all. So yeah, so let's take a little look at it. It's not so useful for math, but I mean, that said, I hope you've realised now with math you shouldn't just be thinking about what might come up. That's not a great way to prepare for the math. The best way to prepare for the math is assuming that almost anything can come up and just trying to make your maths always better, always extend it, always broaden your horizons for the kinds of questions you're doing. So the step papers are good for practicing the big questions on the mat. I would say look at step 1 and step 2 mostly, and yeah, this one's from step 2. This one couldn't come up really on the mat because of like the nature of what it's asking you, but I mean, that said, the difficult bits really are quite similar to the kind of like algebraic understanding. The depth of like your skill in algebraic manipulation needs to be really good for the math, so in that sense it does help you practice it. Okay, and if you are doing the math, I'm going to be doing question 8, I think, from 2014 next, and that looks much more like a math question. So look out for my next video. I'm going to do a few in the next couple of days. Okay, so let's get on with it. Given that y equals xu, where u is a function of x, so it's much more like y equals x f of x, really. You want to see it like that because that's what it really is. We've got to differentiate it, yeah? Now, if you're differentiating something like this, you will need product rule. Yeah, you need product rule because we've got a product of two functions here. And so dy by dx is going to equal, well, we're going to differentiate the x, we're going to get 1. And remember as well, what we're doing here is d by dx to each term. Now you're going to differentiate the x, you're going to get a 1. You're going to times it by the other side undifferentiated. So we're going to differentiate the x, going to get 1. We're going to times it then by u. Then we're going to differentiate f of x, which is our u, yeah? Now, you could call it f dash of x if it was f of x, but we've called it u, so I'm going to call it du by dx, and I'm going to times it by the other side undifferentiated. That's why you get here dy by dx, and I hope it's clear. Let me just make it a bit clearer. Dy by dx equals u plus du by dx x. Yeah, it's a really important fact that do not treat u as if it's a constant. It's not. It's a function of x, and that's why it behaves like this. It's becoming good with manipulating, with differentiating with respect to different variables, and using lots and lots of different variables, differentiating lots and lots of different variables with respect to x is a really important skill in the further maths course. So you want to get comfortable with these kinds of things. So that answers the first part. Okay, and then it says use this substitution to solve this differential equation. Well, brilliant, because this is step 1. This is really just a normal differential equation to solve. In further maths, you do actually learn new techniques like integrating factor for solving differential equations, but really in single maths all you've got is separation of variables, so we know it's going to end up being a separation of variables problem. Now that dy by dx I can write as u plus du by dx x, because they want me to use this substitution. They've asked me to do it, so I must follow their instructions. And then 2y, well, that's going to be 2xu plus x over xu minus 2x. Notice every term there has got an x in it. In other words, I can factorise out the x and cancel it. So I'm going to have du by dx x plus u equals 2u plus 1 over u minus 2. I'm naturally going to take the u onto that side. So I've got du by dx x equals 2u plus 1 over u minus 2, but I'm going to be taking away a u. Well, I might as well make sure it's got a common denominator, so let's make it u times u minus 2 over u minus 2. And so what have we got? We got du by dx equals, well, we're going to have minus u squared, then we're going to have 2u plus 2u, so that's going to be plus 4u plus 1 on the top and u minus 2 on the bottom. Okay, this is a classic separation of variables. If it's in step 2, it must be separate the variables. So, okay, u minus 2 over minus u squared plus 4u plus 1 equals 1 over x dx, and then integrate both sides. That's the separate the variables technique. You want to get really comfortable with that. Now, does the bottom here differentiate to the top? Almost, because this gives me minus 2u plus 4, and I've got positive u minus 2. Well, if I was just to just multiply the top by minus 2, I would have bottom differentiates to the top. So if I put a minus a half outside, that will compensate with the minus 2. And I wouldn't normally do this many steps, but I just want to show you that you can see, yep, indeed, the bottom does differentiate to the top. Oh, look, I missed out a du there. That's shocking. Equals ln x plus c. But let's call it ln k, just because everything's going to have a ln in it. So we've got minus a half ln of the bottom, because the bottom differentiates to the top now, equals ln xk. Yeah. Okay, cool. Now remember, we've got initial conditions, or we've got a point basically that the curve goes through. So that's x is 1, y is 1. Sorry, x is 1, y is 1. And as y equals ux, u is also 1. Yeah, I can just use y equals ux for that to establish u, and I'm just going to plug it in. I'm a big fan of plugging in those points as soon as possible. We get a minus a half ln, and then minus 1 plus 4 plus 1 is 4, and then we're going to get ln k here, aren't we? And so as we can move that up as a power, 4 to the power of minus a half is a half, and so k is a half, and so we know that the answer is minus a half ln of minus u squared plus 4u plus 1 equals ln of x over 2. Cool. Now I've just got to rearrange this into the format that they'd prefer it, because they asked the answer in the form of a quadratic in x and y. Well, that means x can be squared and y can be squared, because it's a quadratic in x and y. So I need to replace u with y over x, and I'm going to move that minus a half over there. So I've got ln of minus y squared over x squared plus 4 y over x plus 1 equals minus 2 ln of that. Well, that's going to be ln of 4 over x squared. I hope you can see that, because I've got minus 2 ln of x over 2, and that gives me that. Yeah, hopefully you can see that. Whoa. Some technical difficulties there. Okay, so now we can ignore the lns or exponentiate both sides, whichever way you want to look at it. So you've got minus y squared over x squared plus 4y over x plus 1 equals 4 over x squared. Multiply everything by x squared, and we've basically got the answer. Plus 4xy plus x squared equals 4. Yeah. What's more, can I point out that these questions are dead easy to check? Yeah, because it's easy to go from our answer to here using just a bit of implicit differentiation. So let's just check that it is indeed the right answer. If we implicitly differentiate this, we get minus 2y dy by dx. Then we're going to get plus 4x dy by dx. So I've differentiated that bit now, and then I'm going to get plus 4y plus 2x, plus 4y, yeah, just plus 4y plus 2x equals 0, and that rearranges into dy by dx equals, you're going to get minus 2x minus 4y over 4x minus 2y. Everything can be halved and divided by minus 1. That's going to give us 2y plus x over y minus 2x. Is that what we started with? 2y plus x over y minus 2x. Good, it is. See, we know we've done it right. And that's the first part, yeah? Now, the second part is not really that much more advanced than the first part. It's very similar, really. So let's have a look at the second part. Okay, this time there's a little bit of thinking first, but essentially they've taught you a new trick. That's the way the examiners see it. They've taught you a new trick of substitution, and basically part 2 is we're going to use some substitutions. But first they've suggested this: x equals capital X plus a, y equals capital Y plus b. For appropriate values of a and b, which we're going to need to choose, we're going to solve this. Now, the minus 4 and the minus 3 on the end are the annoying bits, so we kind of want rid of them, and that's the whole point of choosing x equals x plus a and y equals y plus b. Now, I did a naive approach at first. I just chose a as, I think, like a 4, yeah, and so I had like x plus 4 minus 4, and I thought, oh great, I've got rid of the numbers. But of course, y equals y plus b didn't disappear then, and I was like, oh, how stupid of me. So then I decided, well, what I'll do is I'll do it like this. I will plug in x plus a minus 2y plus b minus 4, and I thought I want the top to end up being just a capital X and a capital Y, but no number on the end. So I made sure that the a, b and the number on the end equaled 0. And then I did the same on the bottom. So I've got 2x plus 2a plus y plus b minus 3 on the bottom. Then I started worrying about this, thinking, well, this is still lowercase y and x. And then I thought, but it doesn't matter, because dy by dy is obviously 1. If you differentiate that with respect to the variable y, b is a constant, you're going to get 1. Same with dx by dx, that clearly equals 1. And hence dy equals d capital Y and dx equals d capital X, and therefore dy by dx equals d capital Y by d capital X. It suddenly occurred to me, yeah, so that's absolutely fine. So I can swap that out, no problem at all. And so what have I got here? I've got dy by dx equals, now if I can just make this x minus 2y and then put on the end plus a minus 2b minus 4, I want that bit on the end to be equal to 0. And the same with the 2x plus y and then 2a plus b minus 3. Now you might think, how do you know I want that last bit to be 0? Well, it's just a hunch. Like, I could solve this no problem with the substitution y equals xu, so maybe I can solve this no problem at all if that and that are 0. And of course then I've just got to solve two simultaneous equations, and the solutions to those two simultaneous equations will give me the values of a and b for which they suddenly end up being 0. And so yeah, that's the bit in this step 2 question where they're asking for a little bit more than just repeating a method. They're asking for some understanding. So if I double a, 2a minus 4b minus 8 equals 0, and then subtract them, I'm going to get 5b minus 3 minus 8 is positive 5 equals 0. And so b is minus 1 there, and a, I think, ends up being 2 when you plug b is minus 1 in there. Okay, so what we've found there is if we had x plus 2 and y minus 1 here, we'd nuke the top and bottom of those last bits, and we'd be left with x minus 2y and 2x plus y on the top and bottom. So I can say, hence, if x equals, sorry, other way around, isn't it? Little x equals x plus 2 and little y equals capital Y minus 1, we end up with dy by dx equals x minus 2y over 2x plus y, and now we can proceed as before. Let y equal ux, and I'll put them all in capitals, and I can use the earlier working here of dy by dx. Well, it's just going to be du by dx x plus, differentiate that, you get 1, so u. And so I've got du by dx x plus u equals, now plug these in and get rid of your y's, so I'm going to have x minus 2ux over 2x plus ux. The x's cancel once again, and you end up with du by dx x equals 1 minus 2u over 2 plus u minus u times by minus u times by u plus 2 over u plus 2, just so we've got a common denominator and we can combine those terms. And now basically it's a differential equation that we're solving. So du by dx, try and keep these x's capitalized, x equals, now what's that going to give me on the top? Minus u squared minus 4u, is that? And then plus 1, I think, over u plus 2. And so u plus 2 over minus u squared minus 4u plus 1 du. I'm just separating the variables here, equals 1 over x dx, and integrate, yeah? Okay, once again, we've got a nice thing to integrate. I'm going to have minus 2u minus 4. Well, that's negative 2 times by the top. So if I have a minus a half out here, ln x, let's do the same thing as before. I keep making my x's curly, sorry. Ln x plus ln k seems sensible. Once again, we've got little x is 1, little y is 1. Don't forget that's little x and little y, not capital X and capital Y. And we already know the connection between these because we got x equals capital X plus 2 and y equals capital Y minus 1. Let's quickly write that down. Plug them in, we can find out that big X is going to be minus 1, big Y is going to be, what to get 1 there, we're going to need that as 2, and U, as Y equals UX, we're going to have U as minus 2 there, aren't we? Okay, so now we can plug these in to find K. So we're going to get minus a half ln. Okay, what we're going to get this time? Minus 4. Let's just plug this in carefully. Minus 2 squared is 4. Minus 4. Then we've got plus 8, which is 4 plus 1, 5. And this is just going to be ln xk, isn't it? Remember, though, that this is a modulus, yeah? And so you're going to get ln of 1, which is 0. So this just simply equals ln k. In other words, k is 1 over root 5. Once you've applied that as a power, 5 to the minus a half, it's 1 over root 5. And so what are we going to have here? We're going to have minus a half. I might even move the minus a half over now and make it a minus 2 on the other side. So ln of minus u squared minus 4u plus 1. Sorry, it's hard on a graphics tablet. I'm getting better, but it is hard. Is minus 2 ln of x over root 5. Cool. We can obviously put that minus 2 in there and make it 5 over x squared. So minus u squared minus 4u plus 1 equals 5 over x squared. I'm going to times the x squared over here. And I'm going to make the u into y over x. So I've got y squared over x squared. Remember, this is just y over x plus 1. Okay, times that through, we're going to get minus y squared minus 4xy plus x squared equals 5. Now just make the switch that x equals capital X plus 2 and y equals capital Y minus 1, I think it was. And so swap capital Y's with Y plus 1, swap capital X's with X minus 2's. Now it's just a fiddling around bit at the end, isn't it? So this is going to be y plus 1 squared. I think this is what I've got. I'm just checking actually by flicking back to what my previous notes said. Yeah, that's cool. Minus 4. Okay, that's going to be x minus 2 and then y plus 1 and then finally x minus 2 all squared. Really, it's just a bit of algebra now. This is going to give us y squared plus 2y plus 1, but all negative. And then this is going to give me minus 4 times xy minus 2y plus x plus 1 plus x squared minus 4x plus 4 equals 5. Okay, now it's just basically simplify it. So what do we got? We've got an x squared, we got a minus y squared, we've got a minus 8x, I think, overall, because we've got minus 4x minus 4x, that's minus 8x. I find it helpful to tick as I go, and I've handled these terms. Okay, let's do the numbers next. Minus 1, minus 4 is minus 5, plus 4 is minus 1. Take away the 5, we're going to get minus 6. Have I made a sign error there? Let me just check I haven't made a sign error. We've got, let me have a look at that carefully. Oh, I've got this last plus 1 wrong, haven't I? That should be a minus 2. Remember, error correction, big part of what you need to do in these questions. So we've got plus 8, plus 4 is 12, minus 1 is 11, minus 5 is positive 6. Now I've dealt with that one, that one, that one, and that one. Okay, I'm going to have a minus 4xy. Let's deal with that one. Now let's deal with the y's. Minus 2y plus 8y is 6y. That's that one and that one dealt with, and then I've got minus y squared equals 0, yeah? Once again as well, can we check this? Yep, just by doing the differentiation, and I definitely did it at the end. I'll just quickly show you, like 2x minus 8 minus 4x dy by dx minus 4y plus 6 dy by dx minus 2y dy by dx equals 0. I rearranged it, and I got 8 minus 2x minus 4y plus 4y over what we got here, 6 minus 2y minus 4x, and if you halve everything you'll find that you get exactly the same as this, but just with a sign switched, I think. And so we know we've got it right. There we go. I'm just going to check on my notes. I have got every single term written down correctly. I think I have. But yeah, that's all you need to do. Okay, so I hope this was useful. It's a typical question for STEP. I'd say even it's possibly a little bit nice now. You go back to 2014, it's almost as if the paper was a bit nicer. But it's a great question, actually, when you're doing differentiation with substitutions, differential equations with substitutions at the end of FP1. It's good to come back to these kinds of questions. There's a few in STEP, they like them. They really do. So anyway, I hope that was useful. Keep up the hard work, and